Hello, everyone, and welcome to the Kahal NeuroKit course on visual reactive programming. Today, we will cover state machines, specifically how we can take what we have learned about observable sequences in reactive programming to modeling experimental task control as a sequence of state transitions that we might to model to describe trials in our task, or operant behavior chambers, or interactive environments for animals. So first, we will start by a quick recap of what we've learned. The special focus on groups, reactive functions, and externalized properties and mapping of properties. We have looked at these topics in the past very briefly, but we didn't cover them systematically, and I would like to take some time to do it here. Then we will review how to represent discrete states in a state machine using select menu. We've covered this also before, but it's worth looking at it in detail one more time, so that we also take advantage of this picture to implement an interactive visual environment using BonVision in the last part of the lecture. We have previously discussed using group operators to organize our workflow and collapse a large definition of a sequence of steps into one node. But we didn't systematically go through the options that group operators allow you. And also we didn't discuss how you can reuse that logic that you organize across workflows and across projects. So we will discuss a little bit about that using include workflows. So imagine you had a processing pipeline that looked roughly like this, a series of steps from image, and what we want to do is group these sequence of steps into our own function. So we can do that using group workflow, right-click group workflow, and we can give it a name. For example, find objects. And then what this allows us to do is go inside the group node and find our definition there. Now, what happens is that often these groups will have parameters inside that we want to manipulate on the node. For example, this function represents a way to find objects, but we often need to configure parameters like the threshold value or the minimum area. So the way to do that is you can externalize properties of the nodes, like, for example, the threshold value and even the threshold type. You can externalize multiple of them. And then, for example, let's say also externalize the minimum area. So when we do this, the top-level workflow will show those properties at the top level. And that also means that if we go back to our top workflow, if you click on that node, the group node, we will see the properties listed there. This is also nice because all the editors that are associated with the properties also get propagated. So the slider bar that is useful for setting the threshold is also available outside. So group workflows are useful, but if you want to use the operation you defined on a different part of the workflow, let's say you had another camera and you wanted to use find objects also in that camera, you'd have to go to the group you defined, make a copy of it, paste it over here, and that would work fine. But now the problem is that if later on you change the definition of find objects, let's say you add an operation or change the finding function altogether, those changes would if you change it only on one place, they would not be reflected to the other copies of find objects, and that makes it difficult to keep track of what we're doing in more complex projects. So to do that, and also to allow building a toolbox of extensions to what's built into Bonsai, the language has the possibility of including defining workflows that you include, not by copy, but by reference. So the way you do this is by going to a node that you already have defined, a group workflow node that you have defined, right-clicking and selecting the option Save as Workflow. So this message might appear if you haven't saved the workflow, since you do need to save it before adding extensions. I'll just save it on top of this one. So if you do it again, it will also ask about probably this message will show up that it asks you to create the extensions folder for the current directory. You can say yes. And then after you do that, if you have given your group workflow a name, that name will be used to name the file of the extension. So if you select save or give a name yourself and save, the group workflow will now be transformed into an include workflow. And include workflows, basically, they work the same way as a group, but they point to a path, to a file on disk. And you cannot go into the group and edit anymore, but you can see the definition of what's in that file by right-clicking and go to definition. The steps of the function will still be there. Now, and the properties will be here. Now, if you want to use find objects again in another place, for every extension you have saved as an include workflow in your project, it'll show up actually in the toolbox under workflow extensions. And find objects is now here. So that means you can drag it actually to another place in the workflow. And these two definitions now point to the same file. The nice thing is you can actually still, even though they're the same file, all the properties you've externalized, you can change them in one location to be different than another location. And BonVision will actually save that as part of your workflow. Even though it doesn't save a copy of the file, it just makes a reference to it. So this is really nice because it allows you to build up these this library of functions that you can reuse. Okay, so another topic that we've discussed yesterday was these reactive functions that require you to provide a definition inside the nested workflow. For example, select many, we saw that we needed to go inside select many and specify the workflow that's going to generate outputs. We talked about different kinds of reactive functions, and these are not all of them. There's several of them that you can find in the group. But we did discuss create observable, for example, which allowed us to create a sequence from a value, but we don't run it. And then we saw that we could use downstream operators like concat or merge or switch to actually run those sequences we create. Finally, there's another operator that we haven't discussed, but now hopefully with this iconography, it's easier to understand, which is called defer. So defer, if you look at it, it has the same output side as select many. So it has a nested workflow inside, and many outputs will come out. So it will run the actual workflow right away. But now the difference is the input side is empty. And why is that? So the difference is that defer does not run the nested workflow for every input it receives. It just runs the nested workflow for every subscription that it receives. And so we were just looking at properties to organize these nested workflows, so allow you to expose the parameters that you want to configure on the top level. You can do this for both groups and for these reactive functions. But there is one more aspect of these properties that I would like to show you and emphasize and discuss a bit what you can do with it, which is you can actually use these externalized properties to change dynamically the values of the parameters. So the way you do this, for example, if we go back to our example workflow, on find objects, we have the threshold value. What if you wanted to change the value not manually, but from another input in the workflow. So the way you start is you externalize the threshold value. And let's say we wanted to adjust it by with a mouse movement. So you can take, for example, the X value here, just rescale it for just for scale to 55. And let's, so if we start the workflow like this, you can see we have a number going between 0 and 255 here. And now if we wanted to change the threshold value based on this number, the only thing you need to do is connect the output, the rescale, to the threshold value. So and that will make a mapping. One subtlety I want to discuss while we're talking about externalized properties and property mappings is about the connection type. So you see here that the connection between the property and the node is dashed, and the other ones are solid. So what that means is that the change in the value of the property of find objects by this threshold value node is independent of the operation of the node. So what do I mean by that? So when we have a connection, let's say between camera capture and find objects, we talked about that this represents a subscription. So find objects will subscribe to the sequence of frames coming from the camera, and then it will react to that sequence in order to emit its output. So for every frame, find objects will run the pipeline and then send the value downstream. When we have, on the other hand, this dashed connection, there is also a subscription, because then this whole sequence will be assigning values to the property from its notifications. But when the values of the properties are changed, find objects will not react to those changes until actually camera capture produces a new value. Okay, so I want to review again one more time how we can think about select many as a way to model a state machine. And we already discussed on yesterday during the recap that to help us build this picture of how we can look at select many as a state machine, because we already have everything we need. We can look at the definition of what a state machine is and what it is doing. And to start discussing it, yesterday we looked at the definition of a state. And then event tend to be just something that happens at a certain point in time, and it's like a singular event. That's usually the way that people think about events. And just from these definitions, we get this idea that states tend to be more extended, and then events are what cause the changes, and they tend to be a single point, a moment in time that then takes you to the next state. So if we take these definitions and we look at the marble diagram for select many, it turns out you can map them relatively straightforward to the marble diagram, these two definitions. So the events can be seen as just the marbles in the marble diagram. So they are notifications. You can think of them as these instantaneous moments in time, these points in time. Now, with select many, we know that for each of these events, for each of these notifications, a whole workflow will be set running. And that workflow that is running inside select many, that has been triggered by the input event arriving, that is what we can call the state. And finally, if we think of the outputs of select many, so they are generated by the state itself. So the state at some point is a sequence that is running, doing its own thing, like playing a file or something like that. And then at some point, it might send an output to the outside, and can be considered essentially an event that might trigger something else. So if you now imagine that you would chain multiple select manys one after the other, the events that come out of this state will trigger a new state in the next select many. So that's how actually you can easily chain sequences of states in a workflow. Okay, so in the last part of this lecture, I would like to talk about interactive visual environments and how you can model them with Bonsai. And this work was done in collaboration with Aman Salim and Sam Solomon at UCL. And the challenge was to create a package for Bonsai that would allow us to easily model these kinds of environments. Visual neuroscience, two types of stimulus are very popular. So one is a 2D stimulus, something like gratings, checkerboards, circles, text on the screen that is presented to map, to do simple tasks, psychophysics tasks, like mapping visual receptive fields or contrast discrimination. The other type of stimulus that is very popular is a 3D stimulus, where the animal is immersed in an environment that surrounds it, and it can navigate through that environment either in an open loop or a closed loop fashion. And we wanted basically to model these two types of stimulus in using the same framework. And the way we thought about doing that is basically by spatializing the 2D stimulus in a 3D world. We can map that reference frame into a sphere that is surrounding the animal. And we can do the same with 3D stimulus as well. The advantage of doing that for both these cases is we can then decouple the modeling of our environment from the display technology we are using to show the stimulus. You can model the entire task on that unified space and then just worry about the output side as a separate problem. This is also an advantage if you want to run the same type of task and across multiple different rigs. Each rig can have its own calibration, can have its own screen configuration, and still your task code the workflow will be exactly the same, which is nice. This includes also things like gamma calibration, gamma correction, and so on. Then the other thing, of course, is we wanted to have a way of just make it easy to create the stimulus and to change their properties dynamically as a function of something we are measuring about the animal behavior. I think it's easier to just show in practice how BonVision is organized. So I will just go through an example, and after looking through this example, I think we'll cover everything that we discussed so far, from setting up visual environments to setting up a task logic using a state machine to mapping properties dynamically, etc. So we can just go through this example, and that will round up the whole topics we discussed. Okay, so to model a interactive visual environment in Bonsai using BonVision, the first thing we need is a display surface, a window. We can create it from the toolbox by using the create window operator. And what this will do is allow you to specify all the parameters of that window, including the color of the window or the screen where it will be displayed, the render frequency, the resolution, and whether it starts in full screen or just as a floating window. So if we just run the workflow with this source node placed, you'll see that a window shows up just in black, which is the default background color. We can change, for example, that background from black to gray, and now we have a gray window. So this window is an OpenGL display surface, which is OpenGL is the library that Bonsai uses to draw everything. And to draw any content now to the window, we need a set of programs called shaders that run in parallel in your GPU to specify where, for example, what color each pixel is going to take, or they can do in parallel transformations to the geometry or 3D models to map how they are going to look like on the screen when seen from a particular angle. And these kinds of transformations are all done through these shader programs. So we need a way to say which these programs can be done and written in many different ways. We need a way to basically say where they come from, and we also need to specify content that is going to be used by the programs, the data that we are going to show on the screen, things like images, 3D models, etc. For now, we are going to use a pre-built package of such resources that comes in BonVision. It contains resources that are used to draw common stimuli in neuroscience, like gratings, checkerboards, circles, simple 3D models, etc., planes. So those pre-built resources can be found by looking at writing BonVision, the toolbox, and there's a node called BonVision resources. And if we drop it following our create window, that node will take care of declaring all the resources we need, we want to load into the window. After that, we need to actually load resources. That's another operator we need. In between create window and load resources, we can actually declare more resources. We could, in addition to the BonVision resources, we could load our own images. For example, if we type in texture resources, this node allows us to declare inside, you could drag into here a list of images you want to load onto the GPU to display on the screen. But like this, we have our window configured with resources loaded and ready to run. So now, how do we actually render something on the screen? So when the window is created, that window is actually running periodically, synchronized to the refresh rate of the screen, two actions, an update frame and a render frame. So we can select that source, drag it onto the workflow, and render frame will basically emit a notification every time there's a new frame to be prepared. Now, the last thing we need to draw something on the screen is to define a reference frame that is going to be used to map coordinates of the stimulus to coordinates of the screen. And that can be done in several different ways. But for now, for us to see and play around a bit with some pre-built stimulus, there is a normalized coordinate frame that basically maps from left to right, -1 to 1, and from bottom to top, -1 to 1. And that range of values will cover your entire screen, no matter what the resolution, and no matter what the size. So it'll be mapped to the entire window. So if we use that node after render frame, that'll take care of that, setting up that mapping. And then we can use draw gratings. So now we can use draw operators to look at. So again, if we look for BonVision, easier. And you look for the draw operations in BonVision. So these are the stimulus that are available with the package for you to draw. So you can draw checkerboard, circle, array of circles for dot field, gratings, an image, a 3D model, quads, and an entire scene, text, a video. So these already cover a broad range of cases you might be interested in. For now, we will draw just a grating. So we can just draw the gratings after normalized view. And if you just drop it like that, when you run start, then we'll have our window reacting to the render frame events by drawing a grating, positioning and drawing a grating on the screen. And the draw grating node has several properties that determine how the grating is actually positioned and sized. So if we change those in real time, because the node is reacting to each frame, we can change the properties of the window. So for example, here, try to position this so you can see better. But if we change the location of the stimulus, change the angle of the gratings, or even the spatial frequency, or we can even set a temporal frequency so that we can see drifting gradings over time. So that will be. So with that, we now know how to draw one stimulus. But of course, what we usually also want is to draw multiple stimulus. So how would we do that? In that case, all of these stimulus need the view definition. So they need to share the view definition. So the way we're going to set this up is by using a subject. Instead of directly connecting draw gradings to the normalized view as we did here, we actually want to organize this in such a way that we can share one view across multiple stimulus. So I'm actually going to cut this node for later and use publish subject here and give it a name such as draw. So this now, I'll draw view. So when this subject now signals when the view is ready to be drawn. So if we now subscribe to it elsewhere, we can paste our draw gradings after it. And as you can imagine, when you now run the workflow, the stimulus is still there in the same place. But now with things set up this way, it's really easy to draw more stimulus. We just need to subscribe again to draw view and place, for example, another draw gradings. And now we have two gradings being displayed at the same time. Okay, so now that we know how to draw multiple stimuli with BonVision, we can discuss about how to modulate the parameter of those stimuli depending on the behavior of the animal. To do this, first of all, I want to get rid of one of the stimuli so that we can keep things simple. And then I set up here an environment with a mini display and a camera that we can use as an arena to play around with these experiments. So to show you what that looks like, I will place a camera now. And if you look at that camera, you'll see I have one of these insects, a button, and an LED from the kit, and also the display screen here. So what we want to do now is, first of all, to make sure the window appears on that display. So I go to create window, I can change the display device to show on the second screen and change the window state to be shown in full screen. So if I do that, we can look at the environment again, and you'll see that now our stimulus is showing up in the secondary display. And we can now, we can now change the parameters in real time as we were doing before. And now everything will be controlled relative to that screen. Now, one problem that we have right away that is very common is that our display environment reference is not the same as the camera. The camera is positioned to the side. So when we move the stimulus to the left and right, that doesn't mean left and right on the camera because of the angle. So what we need to do, for example, if you wanted this stimulus to follow the position of the animal as we move it left and right, we need to define that we need to align the two spatial reference frames. So how do we do that? That's one problem to solve. The other problem is we need to track the animal. That's easier. So let's start with that first. Okay, so to track the animal, we already know more or less what we do. So let's create these color segmentation pipelines and try to find the animal, isolate the animal color, selection, and hue. So that's pretty good. We can then find contours. And now we can, from here, take the centroid. Now, to stop things from growing too complicated, let's go ahead and group this workflow as our object tracking workflow from where the centroid comes in. Okay, so now one problem that we have is that our camera is not aligned to the screen as we were discussing. So if we drag the centroid to the image, you'll see that as I move the animal from left to right, this is not left to right on the pixel space on the screen. So it will be hard to map the position of the animal to the position of the stimulus. So how do we solve this problem? There is a vision node called warp perspective that allows us to correct the perspective of the camera based on a set of parameters that we define. The nice thing about this node, the way this node works, is that the way you set the parameters is actually quite intuitive. So you can go to the source here. There's a specialized editor that basically allows you to define the perspective transformation by dragging the corners of the square where the image is originally mapped. And what this will do is basically make sure that whatever you define as the perspective source, all the pixels in your original image be mapped to the corners. So as you slant the perspective of this quadrilateral, the perspective of the image will change accordingly. So what we need to do is, if we think that the reference frame of that we want to align to the screen is the floor of the arena, so that left and right becomes now the left and right in the floor of the surface. What we need to do is align these corners to match, so that this left corner should be the left corner of this space over here. The right corner over here should be mapped to the right corner over there, and this should point to the bottom. So what we need to do is basically rotate this whole quadrilateral around, so quad around. And as I do that, we will see, line it like that, surface, let's line it to this surface over here. So as we map the space correctly, you'll see now that in the corrected image, so this is our mapped perspective, remapped perspective. And on now the output of warp perspective, you'll see that as I move the inset from left to right, now this is actually reflected on the left to right correctly. So I put the centroid tracking here. Now I actually am moving this position of the center of the object left to right. So that now means that we can take the X position of the centroid to control the position of the gradients correctly. We need to do one last thing, which is we actually should look at the actual range of values that is coming out. So left is going to be 230 more or less, and total to the right will be close to 600. So let's say between 200 and 600 is more or less our range for rescaling. So we now know that in stimulus space, we go from -1 to the left to 1 on the right. So we can actually rescale that completely to go from 600 on pixel space, from 200 to 606 pixel space, and from -1 to 1 in our stimulus space. And if we do this, now we can actually externalize the location X of the gratings and just plug the rescaled position in there. And if we do this, now we see that the stimulus is actually correctly chasing the animal around. Okay, so now that we know how to modulate the parameters of a task in real time with the behavior of the animal, we can try and create a little task with conditions and rules to make things a little bit more interesting. So let's make a hunting task where whereby we want the stimulus to be triggered only when the animal arrives at a certain location. And then the stimulus will appear, will chase the animal around, as we saw before, but then the animal can also get rid of it by pressing the button. So how would you do something like that? First of all, before we start making more complicated logic, I always highly recommend that we separate our inputs and outputs very cleanly from the rest of the workflow. So I will start by doing that now, and also defining the two missing inputs we need, which are the triggering on the area and the button press. So to begin with that, we are first going to decouple our tracking of the animal positions. We'll create a subject here and give it a name of object position. And now we can decouple the connection from the stimulus. Of course, we can reconnect it to our subject we just created, but now things are a little bit more independent. So now everything is working as before, but now we want to add in the tracking of the position. And one way we could do it that we explored in the worksheets is we can do a crop here. We can do a crop here, and we could define that area of interest by defining a crop, a certain area, and then we could process the pixels there to detect the presence of the animal. But we want to do it in a slightly different way by creating a rectangle and doing the test directly on the centroid, just to show you how this is done. So we can, to do that, sort of externalizing the property, we will create a property source from the region of interest. And what this option does is it creates the rectangle itself. And rather than assigning it to the property in the node, you just have it as a notification, a value that you can use in the workflow. And the nice thing about this is that the current value is actually copied, and also the editors, again, are still copied. So this will work exactly like the crop node, but now it'll create the rectangle. So if we now get rid of the crop node, connect the image to our region of interest, for each frame, we'll get a new rectangle to test. And we can still manipulate the position of the region by moving the editor around. So the missing step is now we have the rectangle that we'll test against. We have the position here. We can actually combine these two using a zip and use a function called contains point to check if the point is inside the rectangle. So this is very convenient for doing just a test rather than having to reprocess the pixels. Again, in a different way, you could just check if the centroid is inside a position. So if we do this, and we look at our region of interest and our contains point result, and we move the position of our object inside, that you will see that when the animal enters the region, the contains point function will go high. So this is now our detection of whether the animal is inside a region. And we can, again, save that as an input by saying this is inside region. So that's another input we would need. So now the last input we need is the button press. And that should be fairly straightforward, but we will still do it. So I have the button is connected to the Arduino, as we did in the exercises, to the analog input of the Arduino. And now when we run the workflow, we have the button press. It's pressed. It gives us a signal continuously of the state of the button. We want to filter the signal as we did in the exercises, then 500, for example. And we want to look at only the transitions. We want this to represent the moment when the button is pressed, not just the true and false value. So we want to set up a distinct until changed node that I believe you've read about already in the worksheets. That basically this node gives us the transitions, changes in state from low to high. And we want only the high transitions. So we now place a condition that this will be our actual button pressed. This is high. And now we can define an input also with this, which is our press. Okay, so now that we've defined all the inputs to our task, we can actually write the logic. So let's start by with an ITI. That is always useful to have as a kind of a stability period at the beginning. We'll put a timer. We will define, let's say, 2 seconds of an ITI. And after the 2 seconds, we will go to the first step in our task, which is waiting for the animal to go inside a region. So to define that, as we know now, we use select many to represent the state, and we'll call the state wait for prey. And now that we have all the inputs defined correctly outside, this is actually fairly straightforward to implement. We just need to subscribe to the inside region stream that tells us whether the animal is inside or outside for each frame. And we just need to wait for the first frame where the animal is inside a region. So what we can do is look for the condition here to make sure that the animal has to be inside, not outside. And then we want to say that we want to take the first notification that the animal is inside. And that will actually end state. We can say that that is the output of the state. And in this case, we don't care about the input at all. It's just a state that we go into. And that's the complete wait for prey state. Now that we know that we moved past, now the prey is inside. So now we can move to the second state. So we add another select many. And this is the actual hunting of the prey state. So we just say hunt prey. And so now inside hunt prey, what we want to do actually is exactly what we were doing here with the draw gradings modulated by the animal position. That's the hunting state. So what we can do actually is just cut this workflow part bit here and paste it inside here. Because basically we want to draw the gratings only when we are in the hunting state. So, and to draw the gratings, we need to subscribe to draw view, to the draw view event that tells us that a frame needs to be drawn from this view. So now it's interesting to think about, given the reactive, given our understanding of observable sequences, that it should be easy to understand that the draw gratings now will not be drawn before the animal goes into the region, because draw gratings to actually work needs to react to the stream draw view. And this workflow is not created or subscribed until the wait for prey produces an event. So only at that time will this run, and therefore it's doing what we wanted to do, which is only do this modulation once the animal is inside that region. And now it's already doing the modulation. So we take the object position that is defined also in a state outside, we rescale it appropriately, and we do that chasing behavior. And now the last bit that we need to do is control what's the end of the sequence. So we actually, in this case, we want to stop stimulation when the button is pressed, and that will end the sequence. So we can also, again, look at our understanding of observable sequences to understand how we would do this. So if starting a subscription to draw view is what gets draw gradings going, then stopping that sequence will also stop the draw gradings from running. So it's fairly straightforward. We literally just take our button press, which is our event, to stop the hunting behavior, and we just say take until the button press. Right? So we can just do like this, and the end of the sequence, this will signal that when the button is pressed, the sequence will stop, so the stimulus will stop. And we want that moment to be also the output of the state. So one we want to move the output here, basically. And again, we don't care about the input so far. But one thing that we need to be careful of, we're not going to do more states from here on out, but we usually want to make sure that only one output comes out of select many. If we say take until and leave it like this, then draw gradings is sending an output every time it reacts to a draw view. So actually select many, the state will be firing many events outside. Whereas we really only want to send an event after the state has ended, is finished. And for that, there's an interesting node we can use if we want to signal the event of ending a state. We can say that we want the last event of the sequence to trigger the output. So what this means is the hunting for the prey will keep responding to events, and then at some point the button press will be triggered, the sequence will end, and then only at that moment last will know that it has the last element, which was the last frame to be drawn of the stimulus before the button was pressed, and that will end the state. So if we run the workflow exactly as it is now, we will see that there's no stimulus on the screen. And now the animal has to go into the state to trigger the stimulus. From this moment on, it's moving, chasing the animal, but then the animal can go and click the button to make it go away. And that's our state. And now because we didn't have a repeat, it doesn't start again, but we know how to solve that. We can just add a repeat here, or even a repeat count, say 5 times. And we could have our little repeating trial. Animal goes in, it moves, clicks on stimulus, and then starts again. Okay, so that is it for today. The example took a little bit to go over, but I think it is very useful because it brings together all the knowledge we gained of bonsai over the last few lectures, and combined with these new interactive visual environments, it should have been easier to understand what the workflow is doing at every step. What we've used subjects, we used groups, we used select menus to define our states. We use the basic reactive operators to control the beginning and ending of sequences. We use take until. We defined multiple data streams that were working together to run our task. And hopefully we can look at this example as kind of a reference for how to set up a little mini task together with several different things going on. And yeah, hopefully this will give you more ideas for projects. And for now, there's still a few more things to cover, a few more advanced topics, but this will wrap up basically the core topics we wanted to convey on this course to you, and hopefully with the remaining worksheets and the projects, you'll be in a really good shape to become an independent user of bonsai. And of course, as always, until the end, you can join Discord, ask us more questions, and we will be around to help recap this and go over any topics that might not have been clear. So feel free to reach out, and see you around.